Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will see more on thermodynamic assessment. Today we will get into the guidelines for optimization procedure. So going to be the contents today. We will see the Gibbs energy optimization, the outline and where it fits, and then see some of the guidelines to do that, especially on the input data. We will focus on the difference between thermochemical and constitutional data and more things about input data, followed by in optimization what are the things to be considered, something about start values, what are they, and how or what can be meaningful parameters, and what is assigning weights, and how the procedure itself in general, and how do we judge whether the procedure is over or not, and what are the way forward after that. Okay, so the map is already there in your mind now, and this is where we are going to use the optimization, fit the models to input data. We have the input data on one side, models on one side, statistical fitting will be done, or optimization. We will be using this word optimization for this. And models, once they are fitted to input data, we get the output of Gibbs energy description. Okay. In the next class, we will actually do a hands-on session on how to do the optimization. So in this class, we will see some of the guidelines to do that. So we will introduce some terms here so that in the next class when we use it and do the optimization, things will be familiar to you. Right, these are the different steps. Enter the input data in a pop file, .pop file. This is the input file. Then enter the models in a setup file. It will have the extension of .tcm. And then go for optimization where we do the statistical fitting, and we will do that till the error comes in the satisfying low levels. Error in the sense, the least square method that we are going to use for statistical fitting will give out some error between the fitted value and the actual value, and that error should come within a certain small levels. Only then we will say the optimization is complete. In making input file, certain things are there to be considered. The collected and critically assessed input thermochemical and phase equilibrium data are entered into this file, .pop file. For every experimental measurement, we call the measured value as dependent quantity that is used as input. There must be a matching equilibrium condition written in terms of the proper state variables. So this is how the state variables will be independent quantities in the experimental condition, whatever we set up, and they will be here taken as independent quantities entered as equilibrium conditions in the pop file, and dependent quantity will be the one which is measured. This is how we have to enter it. I will show a couple of examples as well. Each data point should also have an associated standard deviation. So from each data point we assign that, because they are used in the calculation of sum of squares of errors. So this is the thing we will be tracking as we do the optimization, whether the model is fitted to the input data or not. When we want to judge the accuracy of that, we have to look at the sum of squares of errors, and this will be calculated based on how much standard deviation we give for the input data itself. Okay. Let's talk about entering measured data as equilibrium in input file. One of the data we will select and see how to do that. So think of the system like this, AB system with this kind of a behavior in the phase diagram. Okay, so in this we are going to find out this Tylin information here. Alpha, beta are there. These are the compositions of alpha and beta in equilibrium, and that is a Tylin information, and at different temperatures we can get that. Usually the entire line will be tracked with multiple Tylin information. So if this data is measured, how do we enter it into the input file? Let's see that. So this is basically the structure from the pop file itself. So Tylin data of alpha plus beta is entered. This dollar symbol tells you that this is a sentence written for your reference, and it is not a syntax or command to execute anything. Then we start entering this data. Let's say these are two different temperature data. One is at 930 and another is 974 Kelvin. So if we want to enter this data in some table form, we have to start with saying that the table head, some number we have to assign for that, so that this can be used to call this particular data. So table head is given in the top and table end in the bottom. This is important to start entering any data, and within that create new equilibrium @1. So this thing will this @ will take up some numbers. Okay, so here we started with 85, right? So that 85 data will be the first data. As we go down, the second data will become 86 and so on. That's what these two @ symbols mean. And this one means that all other phases except the phases entered here are suspended. This is important to make this equilibrium calculated correctly. So this other phases are removed, only these phases are fixed. Okay, change status of phases alpha and beta, fix 1, meaning alpha and beta are forced to be stable. Once we do this, then we can set condition. What we have done in the experiment will come here. Okay, what we have done in the experiment is keeping the temperature constant. Let's say the temperature here and here is these two values 930 and 974, and it is a isothermal heat treatment to get the phase equilibrium information. So when the samples of any of these overall compositions are selected and they are heat treated at these two temperatures, inside them two phases appeared, alpha beta. After equilibration their compositions are measured, let's say through EPMA kind of measurement, and that's the experiment. Therefore temperature is constant in these two cases. Therefore we will enter temperature as the condition. Temperature is equal to @1. @1 means that in the table below, the first column is the temperature value. Okay. Then :5 is the standard deviation for the temperature values. So this 5 is the value for the error value for this temperature. Then pressure equals P0. This P0 is assigned well before starting the entire POP file in the very top. I have not entered it here. This P0 is the atmospheric pressure, let's say. Okay. Then experiment value. So the observations are entered here. X alpha comma B, meaning the content of B in alpha phase, the mole fraction of that is entered here, and that is in @2 and 3. Okay, @2 is this column. This is the composition of the alpha phase in percentage in mole fraction of B, and this is the error associated with that. You can see @2 : @3. @3 is the error. The column 3 has errors for this mole fraction. Similarly, for beta phase, the B content and its error are given here. And this is how you complete one experimental observation entering into the POP file. Now what about this point here? It looks like a eutectic reaction. This is how the eutectic reaction is entered. Three phases are in equilibrium, right? And create new equilibrium. Just one value we are going to enter, so only one number we are directly entering. And change status. We are going to assign alpha beta liquid phase to be fixed, because three phases are to be there in equilibrium at this condition. So set condition P equals P0. That's the only condition we are forcing, and other things are entered as the experimental data. Okay. And here that comment thing, in the previous slide also we had this comment here and a label. This is also important because this YYYY stands for year. AU1 is author 1. So you can keep year and first author name followed by a number. This kind of comment you can use. This is also in a way referring to this particular data set. Okay, and we can also use label data, AU author 10. So that's how this label is given for this particular data set. We can use these things to refer and call this data set. Right. So here also we have this label data and comment symbols. Then we have this experiment. Temperature of this value, let's say this is the temperature of eutectic transformation, and there what is the composition of beta, what is the composition of alpha, and what is the composition of liquid. These things are given here directly. This is how you enter a eutectic reaction data. No table kind of thing here, only single data. Right. A general guideline for this kind of data, which one to be dependent, which one to be independent. The choice of dependent and independent quantities while defining an experiment is critical for the progress of optimization. Let's say we have this line and this particular data here. This is a horizontal boundary, right? We said we want to measure this. So if you do a DTA, just keep increasing the temperature, it will give a signal on at this particular temperature that there is a transformation, right? Similarly, if you want this data, we have to keep things at isothermal temperature so that we can get this data and possibly this data also, or do some metallography at all these different compositions at one single temperature. We will see that before this there will be single phase, beyond this there will be two phases, right? So we will keep the temperature constant and measure this value, whereas we want to measure this value, we increase temperature in dTA and observe the phase transformation here. So in this way, a general guideline can be a vertical boundary, which is this kind of thing. Their temperature can be constant and composition can be the variable in the experiment. And in the horizontal boundary, this kind of thing, temperature is going to be increasing, so temperature is variable, and composition is constant, one single composition, we are increasing the temperature. Okay. Now comes one of the important ideas in Gibbs energy optimization. What kind of data is good? Okay, phase equilibria data we have, thermochemical data also we have. Which of these two things are better? Phase equilibria data is implicitly linked to Gibbs energy and thermochemical data is explicitly linked. Okay, implicitly linked data is difficult to optimize, we will see why. Estimation of Gibbs energy functions from phase diagram data is an ill-conditioned problem. Therefore, phase equilibria data should almost always be supplemented with thermochemical data. So, to understand, recall this G curve with three different L parameters. We have seen this delta G mix. This is the actual behavior of a phase, let's say. And to model this, we have to have three different L parameters. Addition of all these things will give this white line. Right. Now, this curve we will take. Okay. And let's bring another phase like this. If two phases are to be in equilibrium, this is the common tangent, and these are the points we get as Thailand information from this. Okay, so let's say this information is available. This Thailand information is the phase equilibria data, right? This is available to us, and from this we want to reverse and come to this kind of Gibbs energy curves. Okay, so that is what Gibbs energy fitting from phase equilibria data is. Now, if these two curves are like this is modeled with some 3 L parameters and this is modeled with certain number of L parameters, let's say, and that is when we get these two kind of curves. Let's say this is the most accurate thing. Okay. If we substantiate with thermochemical data, whatever Gibbs energy we get from thermochemistry, that Gibbs energy is actually resembled by this line, let's say. So this is the correct line, correct behavior of alloy system for these two different phases, right? Now I can get the same Thailand information with another set of two curves, you see. Now let's say this is the Gibbs energy of this phase, purple one, and the white one is here. Okay. Now if I don't have any thermochemical data to substantiate this, this is also correct, because based on my phase equilibria data, the Thailands are reproduced with this. Okay. But actual Gibbs energy is not this. Actual Gibbs energy is this. Okay. So this can come only when we also use the thermochemical data to optimize. If we don't use thermochemical data, we will end up with any different kind of Gibbs energy curves like this. Which are the L parameters to be used, how many to be used, and all those things, there are problems. Okay, so estimation of Gibbs energy functions from phase diagram data is an ill-conditioned problem due to this kind of reason. And also, if you see a small change in this constitutional data, some kind of error, let's say, even that can cause severe changes in the Gibbs energy curves. Okay, so you can see for the same data points itself, I can get different Gibbs energy curves going across. So if the data is slightly wrong, then I can get very different Gibbs energy curves. Okay, so there is a huge scope of error for when we use only constitutional data. We have to be careful with that. Right? So now some guidelines for input file are given here. Direct experimental data to be used or an estimated data to be used. What are we talking about here? Some of the data that we use, let's say some thermochemical data, comes from some particular experiment. In that experiment, the direct reading is not for this particular quantity. It is for some other quantity. From that, this quantity is estimated, and this is used in the POP file. So if that is the case, is that good? Which one is better to use? Okay. If the software can handle the directly measured value from the equipment, that can be used. But if the software cannot handle that, then we have to use this estimated data, right? So if the software is capable of handling direct experimental data, it is better. If not, we have to be careful about using the estimated data. Okay. It is usually best to use directly measured experimental data as input for optimization. Data that are derived from measurements may not always meet the statistical requirements of least square optimization. This is the reason why we do this. An effective optimization program should therefore allow input of the actual measured quantity, not just the derived one. This is an example given here. EMF value E instead of calculated activity. We know from E we put the minus N of E and calculate the activity from that. So this particular procedure basically allows us to use the activity into the POP file. But activity is an estimated quantity from the E which is measured. If there is a provision to use E directly, it is better. Okay. In some cases, using the measured quantity directly is not possible. This could be due to software limitations or mathematical constraints. For example, this one, CHEMS, Knudsen cell mass spectrometer, where the measured quantity is this, the ion intensity ratio. This is used to identify which are the vapor species that is coming out. But what we are using is activity or activity coefficient in the optimization. Okay. There is no way to use this. Okay. E at least can be used in some way. We can rearrange the equations and start using E, but there is no way to use this I. Okay. Okay. These are some general guidelines. Success of an optimization depends on the following: the selected models and the selected experimental data, the number of model parameters, what parameters can be meaningfully optimized using the selected experimental data, and what are the starting values for model parameters, the order in which parameters are optimized. All these things are important. We'll see them. Start values, what are they? The optimization program calculates the dependent quantities at the given equilibrium condition using an initial set of variables known as start values. Okay, so what are the start values? If you start the optimization procedure, you have the input data, you have the model parameters, the variables that are there within the model parameters. So these variables should get a number now fitting to the input data. So when we start doing this, it's an iterative procedure. We need to have first some values for these variables. It will check whether that variables are able to at least roughly calculate this equilibrium condition that we entered in the input file. If it is able to calculate that, then it will keep on optimizing it to minimize the error. Okay. But initially, if it is not able to even calculate the equilibrium, then the start values are really bad. Then we have to keep identifying what are the different methods to give a very reasonable start value. So these start values basically are the ones which are the variables are the ones which we are trying to optimize, get a number for, and to start with we'll have to give some start value to that. So software can actually have a start value on its own. If it is not, then we have to give that. These variables are then adjusted step by step. This is an iterative procedure until the weighted sum of squares of error reaches a minimum. This is where we are heading to. Then a significant amount of effort goes into selecting suitable start values, okay, so that the program can successfully compute a corresponding value for each experimental data. So this is a difficult part, getting the right start values. Okay. The optimization software usually includes tools to generate start values for the model parameters. If these built-in procedures don't work, that's where heuristic approaches may be needed. In some cases, parameters from a similar system can also serve as useful start values. Something about what are meaningful parameters and data. This is some extreme cases. Okay, let's see that. It is pointless to optimize certain parameters if there is no relevant thermochemical data that give them significance. As thermochemical data should be there in order to optimize certain parameters. So you have some parameters modeled, it should have some connection to some Gibbs energy data, some thermochemical data. If it is not there, it is difficult to optimize. The relative standard deviation of a parameter can be used to judge its reliability. A large value indicates that the parameter is poorly determined and should therefore be excluded from the optimization. So it's meaningless to do such parameter optimization. Then during optimization, some experimental data may prove difficult to fit. Okay. Then such cases usually suggest that the data are erroneous and they should be carefully re-examined. The input data itself should be re-examined. Okay. Then during the optimization procedure, there is something called assigning weights to this input data. So what happens is, once you bring some input data and bring some models, we will not actually take all the input data at one go and all the models in one go and try to fit. We will take them step by step. So if you take one set of input data and one set of model parameters and try to fit them, that time we have to assign some weightages to this input data. Okay, the ones that we are taking, we can assign some weightage to that. For the others, we can assign the weight as 0. And for this also, if we think some data are really good and that particular data should be fitted really nicely and there should be very less error when the model fits to that particular data. If that is the requirement, we can assign higher weight for that. And similarly, if we feel some data is poor, we can assign lower weight to them. Okay. During optimization, weights are assigned to each data. The higher the weight of a datum, the better the fitting should be to that particular datum. If required, input data should be corrected for systematic errors. Using too many data of one kind can make the optimization biased. Yes, the fitting will converge more towards that particular data. Okay. To avoid it, weights of such data may be reduced. This is what we do. Okay. So now something very general about optimization we are going to see now. There is a significant scope for subjective decisions and judgments which requires expertise and experience. Okay. Knowledge of thermodynamics, physical metallurgy and statistical fitting would really help. The optimization is an iterative procedure. Okay, so calculating the phase diagram during different stages of optimization and comparing them with the experimental results is useful. We have to keep doing this in order to see where our iterative procedure is heading to. You can understand many things from that. It may reveal several non-conformities, metastable regions becoming stable, etc., which may demand a change in the optimization strategy. Okay, we need to rethink what we have been doing and possibly start everything in a different way. All those possibilities are there. The results may sometimes force the assessor to alter models, change essential data sets and revise weights. So all these things are done. You can sense how difficult it is. There is a lot of scope for subjective decisions. Therefore, the output also there is lot of scope for improvement many times. Okay. So once the optimization is tentatively complete, okay, what we need to check is the extrapolation characteristics. Okay. After the tentative completion of optimization, it may be necessary to perform some calculations outside the range of experimental data. Okay. To check the Gibson-Edge description as acceptable extrapolation features or not. For example, calculate the phase diagram for a wider temperature range, even if the input experimental data do not cover the whole temperature range. Okay. So this can be tried to see the extrapolation features. And the decision to conclude an optimization generally depends on a balanced combination of the following factors. 1. An acceptable agreement between the calculated and experimental data, meaning the sum of squares should be within some minimum number. Reasonable magnitudes for the parameter values and their standard deviations. Then good extrapolation characteristics should be there. Okay, once these things are checked, we can conclude. But you can always keep in mind that an optimization is usually prone to further improvement. Whenever new data become available, existing thermodynamic description should be checked for its ability to predict it. Let's say with these parameters that you have optimized, you are making a phase diagram and there are certain regions in which there is no experimental data available, let's say. And if somebody reports a data in that particular region, if their data fits with your predicted phase diagram, then your description is much better. This is how you can conclude. If not, you have to improve the database. More importantly, there are always specific difficulties associated in different systems. Thank you. I hope the lecture is useful. See you in the next class.